Okay, so we're going to talk about dynamic programming today. First, I'll give you a very quick introduction to what it is, but it's so abstract that it's not very helpful to stay at that level. So then we'll go through 4 examples of it. And the 4 examples will one by one show you the different concepts and the difficulties that arise in building dynamic programming solutions. So first of all, what does the name mean? It doesn't mean programming in the traditional sense of coding, or rather in the modern sense of coding. It means it in the traditional sense of filling in tables. Programming used to mean you take a table and you fill it in with either numbers or other things. That's what programming in this scenario means, and it's dynamic in that you're filling in the entries of a table based on previous entries of the table in a dynamic manner, as opposed to something that is predetermined and static. So that's what dynamic programming means, and that's so general that it doesn't seem like a very helpful name, and it really isn't a very helpful name. So the recipe for a dynamic programming solution usually is, again, too abstract, but it's worth writing down. So the first step in any dynamic programming solution is to come up with recursive substructure. So you have your problem, and it's whatever problem, and you have to somehow split it up into smaller subproblems. And that's really the general level that dynamic programming deals with, but it's super vague, right? What does that even mean? Split a problem into subproblems. But it really is just that you can't really explain it more than that other than through examples. So split a problem into subproblems. And very, very often, what this means is that you're actually defining the problem as something that is recursive. So you have often a function, and then the subproblems become calls to that function with different parameters. Recursion is a very natural way to take a problem and turn it into subproblems. But it doesn't stop there. That's why if you go into some books like the CLRS, you'll keep hearing this over and over again. But really, the working knowledge of dynamic programming is recursion. Okay? So then once you have your problem settled down into subproblems, there are some very standard techniques like memoization. And I'm not misspelling that. It really is memoization. It's dynamically filling in a cache. So once you have your regular recursive problem, you'll start caching it so that its runtime improves. And we'll see that through an example. Then once you have that done, you can actually undo the recursion. You look at your problem and you see, OK, I'm actually filling in this cache, which is a table. So this is, you might be more comfortable with calling this caching. And a cache is really just a table, and you're dynamically filling in this table. So in the third step, you can just fill in the table yourself without having anything to do with recursion. Okay? So then that's really called dynamic programming. These are the 3 steps you take. And the first one is by far the most difficult one, in that it requires the most amount of creativity and the most amount of knowledge about your problem and just smarts, basically. Like, it's hard to take a problem and turn it into something that's recursive and amenable to dynamic programming. So I'm going to go through 4 problems. The first one is going to be Fibonacci numbers. For this one, the recursive definition is just already given. So then we can see how that memoization and dynamic programming work. The second one is going to be finding maximum windows in an array. Find max window in a real number array. This one, it's a little more tricky to find the actual recursive definition that will get you your answer. So the first problem, you need some creativity, and then you'll see that. Then, so there's one more step, sorry, backtracking. In case of optimization, which should always, in case of optimization. Okay, so what is the backtracking step? It's a it's a pseudo step. I wouldn't. This is the heart of dynamic programming. This step is really just an addition. The times that it arises are when you're using dynamic programming to solve an optimization problem, and then the dynamic program will often just give you the value, the optimal value of the optimization problem, and then you actually want the argmin or the argmax. For that, you need backtracking. You actually need to go back and see how you filled in the table to get the argmin or the argmax. So in that case, you have a little bit of extra work, and we'll go through that. And for that, we're going to look at apple picking. So apple picking will let us see how to use backtracking. And finally, for runtime analysis, we'll look at coin collection. So these are 4 problems that we're going to solve using dynamic programming. Okay. So the very first problem, Fibonacci numbers. It's probably, you've all probably seen the definition of Fibonacci numbers before. It's immediate from, the recursive definition is immediate from the problem statement. So the Fibonacci numbers are a sequence of numbers f0 through infinity, and f0 and f1 are equal to 1. And then f of n is simply the sum of the previous 2. Okay? Nothing fancy about this. The numbers grow really fast. They grow exponentially, where the base of the exponent is the golden ratio, and the problem is just to compute these. Right? So I just want the first n of them. Okay? So here, there's a very trivial recursive definition. You just define f of n, right, to return f of n minus 1 plus f of n minus 2. And with just this if statement, if n equals 0 or 1, return 1 else. Okay? Who can tell me the runtime of this algorithm? So we just took the basic recursive definition, put it into a pseudocode. What's the runtime of this algorithm? At least vaguely. Is it polynomial, subpolynomial, super, anyone? O of n? No. Why do you think it's O of n? So there is an O of n solution, but this way that we wrote it down is stupid, right? This is a recursive definition. So we're trying to just take a recursive definition, put it into a function, and call a function. This way it's actually exponential. So what will happen is the runtime looks like this. So you start out calling f of n, and then f of n will call f of n minus 1 and 2, and then f of n minus 1 and 2 will again call 2 functions, and this will create an exponentially growing nested hierarchy of calls. And that's no good. So f of n creates creates a call to f of n minus 1, f of n minus 2, f of n minus 3, f of n minus, it should be 4, 3, f of n minus 2, f of n minus 3, da 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 da, right? This, and then you have to go all the way down, evaluate to get to a base case, come all the way up, exponential.
Why don't they just go out?
Why don't they just go up? I don't understand. Why don't they just go up? What's going up?
If you want to know fn, why don't you just go from f0 and f1?
If I want, because I'm trying to go from I'm doing it by recursion here, right? So this is, there are a million really easy, there's a constant time solution to this, right? There's just like a formula that is closed form, right? We're trying to do it from the recursive definition, right? So I'm not pulling your leg here. This is educational, that's all. So the point is that if you take a recursive definition and just be stupid about it, you'll shoot yourself in the foot. Now, how can I fix that? what's the problem here? I mean, what am I seeing? I'm seeing f of n minus 2 here and here. Why? I don't, that's stupid, right? If I already computed it here, why am I going down the tree all over again? Right? So this is where caching comes in. This is where memoization comes in. Right? So instead of being silly and calling the full tree, what I'm going to do is first check if I've computed this before. So let's call it G of n, and it's just an array that is pre-allocated from 1 through n. It's, at first it's unallocated. So then instead of just doing the recursive definition, first we check if we've computed it before. So we get f of n, we're trying to compute it, we have the base cases, fine. But then we don't want to just recurse, we want to check if it's been computed. If this value of f has been computed before, then just return it. Return g of n. We're going to store the computed values here. Else, g of n equals f of n minus 1 plus f of n minus 2. Here, then, we recurse if we have to, if we absolutely must. And we set the computed flag to true, just so that we know that it's been computed and never do it again. Computed n equals true. And again, computed is some array of booleans 1 through n. Very hacky pseudocode. Now what happens? Right? Now we have this check mark that says the nth Fibonacci number has been computed. Don't redo it. So then when we're here, one of these will have been computed before the other, and so that entire subtree will become unnecessary. Right? And we'll have at most n of these calls, so there'll just be n invocations of the recursive function. So already we just went from exponential, which is stupid, to linear. Right? So this subtree goes away. And this subtree probably goes away. Then there are no repeats. Okay? It depends on the order that you're compiling. Well, yeah. So you basically won't get repeats. Okay? So you went from, okay, so that's memoization in its most basic form. Right? And what happened is that we are filling in this array using the recursive function. Right? This array is getting filled in every time the base case is not hit. This computation's done. The G array, which is our memoization table, is filled in. Why don't we just fill that in ourselves without doing recursion? We can do that. We can even, so this algorithm has all the, it's sort of opaque. You have to think about it in terms of trees and you have to see what's going on. And you don't need to do that, right? You can just fill in the array yourself. So instead of this recursion, what we'll do is dynamic programming. So we'll actually fill in the array ourselves. And we can just do it by realizing that if we had computed them in order, if we computed F2 before F3, then we have the values necessary to complete F3, and then do F4 and F5, and that's it. You always have some order to which the table is being filled in. So you have to look at your recursive definition, see how it will fill in the table, and do it yourself. So a simple for loop from I equals 2 to n will do it. G of n is equal to G of n minus I. Sorry, G of I. G of I is equal to G of I minus 1 plus G of I minus 2. And this won't create any recursion or anything because you're exactly making these ready for computation for the next step. And that's the linear time solution you were talking about. You're like, what are you doing this silly thing? This is the essence of a dynamic program. What will happen is that you'll take much more complicated recursive definitions, and it just so happens that those are the more natural ways of thinking about the problem. Then you'll either stick it out with memoization and say, this is good enough, my algorithm runs fast enough, I'm tired of this problem. Or you'll then even go one step further. You'll fill in the array yourself, and you'll gain an order of probably like twice faster, because suddenly you don't have all these recursive calls. But in asymptotic notation, you're not changing anything by filling in table yourself. So that's, you don't actually need to do that, but we're going all the way here. So any questions about this so far? I'm going to go on to the next solution. So this was pretty easy. There's actually like a closed form formula for the Fibonacci numbers. So purely an educational exercise. All right, so the next question, the next example, will actually need some creativity to write down the recursive definition. It won't just be given to us on a platter. The question is, I give you an array, and it's filled with numbers that are positive or negative, real numbers, and I'm asking you to find in as fast a time as possible a window of this array, meaning a start index and an end index of this array that has maximum sum. All right? So what did I call this problem? Maximum window or something? Yeah, okay. So maximum window. So you have an array from 1 through n. Real numbers, most important that some of them be negative, otherwise the answer is trivial. And here's a really simple algorithm for this, right? You can just loop through all. Is the problem definition clear, by the way? Anyone not clear about the problem definition? Okay, so just loop through all pairs. For ij pairs, compute sum from I to j. Right, and compute sum just takes a through I through ai through ij and adds them up. So we're gonna get down to a really efficient algorithm for this. We're never going to go into exponential territory in the stupid solutions, just like we did in the Fibonacci case, but we're going to go down from n cubed down to O of n. So it's possible to find this maximum window in O of n time, in linear time. So what's the runtime of this thing? It's going to go over all pairs. That's already n squared. Then it's going to compute sum, and that's another order n. So that's n cubed. No good. Now, we can optimize compute sum. Right? We can sort of compute the integral, or we can compute a running sum of the AIs. And then in this step, just subtract the two running sums from j and I. And that will give us the sum in a really fast way, in constant time. So that will be O of n squared. Still no good. So now comes dynamic programming. We need a recursive definition of this problem that somehow makes it faster.
How would you do it in constant time?
Compute sum.
Yeah, the partial sum, what you said.
The partial sum, this partial sum.
Yeah.
In constant. So if you do some pre-processing beforehand, so you have this array called partial of I. This will be the sum of the array from 1 to I. Then when it comes time to finding a window, you just do j minus I. Okay? So this you can compute in linear time. And it's a pre-computation. What's up?
So when you do the sum, it already costs O n time.
Yeah, but I think it's not.
But it's not every time. You do it once before you start anything.
So you do it before for one.
Oh yeah.
Mhm. You do the sum once before you do anything else. Then you have partial available to you. And then you do the subtractions or lookups. Okay? So, but that's, the real problem is this part. This, for all pairs, you're really just brute forcing the problem. It's not satisfying at all. Okay, so here's the part where you really need some creativity. Why? You might not even think this problem is easily doable in O of n time. But it is. Okay, so here's the recursive definition that's going to come save us. The definition is going to be, I'm going to define some new array called M of I. okay? And M of I is going to have a very delicate definition. M of I is going to be the size, i.e. the sum of the largest window ending at I. The window's end must be at I. It's very important. Okay. So now, with this definition, I claim I can compute the original problem. Well, the original problem, its maximum window must have ended somewhere, right? So with this definition, if I take M of I to be the largest window ending at I, if I then take a max of M of over all I M of I, because the original window has to end somewhere, and this one is all about the ones that end in a particular place, just sum over all the endings possible, I'll get the solution to the original problem. Okay? So now suddenly I've taken the problem and made it a little different. But this problem lends itself very nicely to a recursive structure. So this is where the creativity came in. You'll get very difficult, complicated problems, and you have to think about how to rewrite them. Okay? So now how do I do M of I fast? How is it that M of I can have a really easy recursive definition that lends itself to dynamic programming? So the way we're going to compute M of I is going to be recursive. M of I, what could possibly happen to a window at ends at I? So forget partials now. You're at a position J, right? Actually, you're at a position I in the array, right? And you're trying to find the length of the longest window that ends at I. Well, what could possibly happen? You could either extend the window from the previous position, because that was the largest window that ended at I minus 1, or you could just start a new window. Those are the only two possibilities. This is, you either extend the largest window that is right next to you.
You add the element.
Or, yeah, you either add this element or you start a new window. You just say the element on its own.
And you use that element only if the previous one was negative.
Not necessarily.
Some of them is less than.
If you basically, you might.
Yes. And you will add something.
Right. So you'll only start a new window if it benefits you. So it's if it's the maximum of start a new window at II, or it's going to be M of I minus 1, M of I minus 1 plus A of I. And that's it. Okay. So now you can just run this recursion with memoization to be sure you don't overcompute things. And this recursion will take O of n time to finish. Why? Because there are only n subproblems, and each one you're only doing a constant amount of work. So this function, you look at it, it's only got n possible things you could throw at it, and you'll only ever do constant amount of work for every one. So then this takes O of n to compute. Then you have the largest sum of any window ending at I in linear time. Then you spend another linear amount of time to find the maximum there. Then you have the solution to the original problem. So the trick here was that recursive definition. This ending at I was everything. So this is what dynamic programming is all about, finding these little things. That's why people publish papers on this stuff, because you can have a really complicated, say, graphical model, and you're trying to train it, and you don't know how you should quite do the optimization. You realize, oh, there's this recursive substructure, and what do you know? Suddenly my problem went from exponential time to sub-exponential or polynomial, very easy. You need creativity to get that recursive substructure. That's why you get away with publishing it. So there's a lesson to be had here, and I forget what. No, that's it. So it was just this. The recursive substructure is what this example is supposed to illuminate. Right? So you're supposed to do hard work to get the recursive substructure. All right, let's pick some apples. So that's
I have a question.
what's up.
So this doesn't tell us what the window is, though, right?
No. But could you tell me how to figure it out?
Yeah. Well, we could pass a pointer to
Yes.
the previous one.
That's backtracking.
Yeah.
No big deal. But I'll bring that up in I guess, a better example.
Okay.
Okay. So am I missing something? No. Okay. So now I give you a two-dimensional array of apples, and sometimes you have negative apples, so sometimes I'll take apples away. So you have you're starting at the top left of this array, and you got to get to the bottom right. And you pay apples or you get apples on the way. You want to maximize the number of apples by the time you get down there. How do you do that? So you have this array. It's more like a grid. It's better to think of it as a grid. And you just have numbers in it. And the idea is to get from here to here with as large a sum as you can. And you can only go to the right or you can go down. Okay? So you have all these decisions to make, lots and lots of decisions. You have as many as there are rows and columns, decisions to make. Because at every point you have to decide between going to the right or down. And that's, you're choosing between two decisions and let's say the array is n by, let's say it's square just for now. So it's roughly order 2 to the 2n decisions you have to make. And so the exhaustive search would be ridiculous, but we're gonna to find the maximum exhaustive search would be ridiculous. That's all but we'll bring this number down a lot. Yeah. So again, there are negative numbers. So you have to optimize and, in a way, look ahead to make sure you don't end up in an area that is maybe completely negative, like full of negative numbers. Okay. And you, again, only down and up, and you end up at the end. So any first step? What's the first step? Recursive or subproblem definition. What's the subproblem definition? This takes a little creativity, more than the Fibonacci numbers, but I would say less than the max window one.
The maximum of what you get out of taking a left step, or sorry, right step or down step.
The maximum of what you get out of taking a
Well,
right. So that's a fair recursive definition, but it's yes, and then you could memoize that, and then you'd be done, right? Right? Because so
So all the values are non-negative, right?
I'm sorry.
All the values are non-negative.
No, they can be negative.
Can we negative?
They can be negative. It doesn't really matter. Yeah, it's not like there would be a trivial solution if all the values were positive or there were some negative. It's not. Doesn't matter.
Because negative will mean that you might reset, right? You might say, okay, I don't want this part at all.
Yeah, but you could add or subtract a million to every number. It doesn't matter.
Yeah, it doesn't. The sign doesn't really matter. The problem remains the same. So what's the recursive definition exactly?
well, I mean, I guess if you're at the end, then return whatever you've accumulated.
If you're at the end, return whatever you've accumulated. What if you're not at the end?
Then return the maximum of taking a step to the right,
Okay.
or taking a step down.
So you're saying let's call best of ij as if I is equal to j is equal to n, then return 0. Because return just what's going to be here.
Yeah.
A of n. And otherwise, you're saying take the max of best of oh, we have to add the current value, right? So
But you want the sum of all the paths?
we want the sum of the path. Yeah.
So why would you return A and N?
You'll see. So what this is really defining is the best sum if I had started at ij. That's what it's really defining, right? So if you start at nn, the best sum you're ever going to get is just that value, right? So that's what I really wanted you to say, is that the one of the ways to write down the recursion is to take the best, is to turn the subproblems into the problem that is starting at ij, what's the best you can do to get to nn. Right, so that's what you just defined. So if we're at the end, the best we can do is the end. Otherwise, we can go to the right or below. So we add the current that we're at, wherever it is, and then we take the better of the best of I plus 1, i.e. go down in j, or best of now there's a little catch here in that sometimes you're going to be out of bounds here, so you can't. So you just have to be careful to if in bounds here. Add an if in bounds for both of them. Okay? Sometimes it's just one thing you can do, go down or go right. Now this, you really should memorize, I believe.
Just fill it in backwards.
Right. Right. Or you can, right, so exactly. So with memoization, how much work are you going to do? You're going to take your function space is potentially all possible values to the first parameter and all possible values to the second parameter, which is what? It's n for each, and therefore n squared. How much work are you doing in each of them? There are no loops here, nothing. It's just a bunch of operations, and they finish in constant time. So you're doing O of n squared work. You have to add the memoization logic. You have to check if you've computed things before, added in, right? But again, that's not going to add any runtime because it's all constant. Right? So that's brought down the exponential runtime to n squared, which is nice. But how do we get the actual path? The actual path itself is a little tricky.
Just to record where the best come from. Like
Perfect. So you can remember one step behind. And as long as you know one step behind, you can start at here, go one step back, recover the whole solution all the way back to the start. And that will give you the maximal path all the way back, all the way down. Okay, you guys. So this is turning out to be easier than I expected. Is there any question? Are there any questions about? So that was backtracking what he just said. Yes.
So I was puzzled by, suppose you start at the bottom right and you want to, you change the problem, right? You start now at the bottom right and you want to move up to the top left, which is, you'll get the same value, right?
So wait, are you talking about a recursive solution, or are you talking about filling a table yourself?
No.
So you say you start at the bottom right, you gotta. Yeah,
So suppose you change the problem,
Mhm.
instead of having to go from the top left to the bottom right.
Oh, okay.
you get the
Sure.
You change it, you start at the bottom right and you move to the top left.
Sure.
So you can have exactly the same recursion starting from you'll get the same solution. You can start from the top left and work your way back down.
Yeah.
But that would suggest that you could also have some algorithm that starts at the top left, even if you start at the top left, and you don't have to work backwards. If you understand.
So you're saying even if,
I mean, this works,
Mhm.
but I was just like, is there a way not to use backtracking in a way? Because you think that because of the symmetry, you could also start from the top left.
if you slightly change the recursive definition to, instead of being the best starting at ij and going to nn, change the definition so that best of ij would mean
The best way you got there from the beginning.
right. If then you could go backwards, and then your backtracking would actually start from the front to the end. But it's the same deal. You're going to get an optimal path in both ways, and you'll get the same value for the path in both ways. There's no right way of doing that. There will be multiple ways to take a problem and break it down into subproblems. So this is one way. Some of them are actually better in that they'll lend themselves to cheaper runtime. Sometimes it happens that you can come up with multiple subproblem definitions. And usually the way to decide between them is which one has fewer parameters and which fewer parameter space, less of a parameter space. But in this case, they're both the same. Which is very intuitive, because all you did was take the problem and start it the other way. So instead of memoization and letting the recursion fill in the table, we could fill in the table ourselves. So we could fill in this best. Best is what? It's just another two-dimensional grid. This is the best grid, let's say. We could start at the bottom left because we know its value from the recursion. The bottom left is just a and n. And then fill in this value and this value. Then fill in this value, then fill in this value, blah, 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 and work our way all the way up until we're done and gotten this. So then we bypass the recursion, bypass the memoization, use less memory, run faster. And call it dynamic programming instead of memoization and recursion. And any questions? I'm going to go on to the last example. This went way faster than I expected. You guys already know dynamic programming, or at least you're very comfortable with it. Yes?
So as it stands now, we could, in every path between 1, 1, and n is the same length, right? So even with negative weights, we could use like Dijkstra's algorithm on this. Is that, I mean,
Yeah.
Yeah.
Yeah, so you could think of this as a graph. And you're finding a path through the graph. But you wouldn't need, it's a very specific graph, so you don't need, it's linear, its runtime is linear in the number of edges in the graph. But Dijkstra's is actually a little more than linear in the number of edges in the graph. So you're winning here. Because the graph is so structured, you don't need to resort to heavy-duty techniques like Dijkstra's algorithm.
Sure. I was just thinking of, because we do have this property that every path has the same length, that's why negative costs don't really matter at all, and why we do Dijkstra's on this, because Dijkstra's only worries about negative costs if the paths are different lengths, right? When you do transformations of the weights.
So Dijkstra's algorithm only works for non-negative, it needs positive weights.
Right, but if every path is the same length, then you can transform it, it doesn't break it.
If every path has?
If every path is of the same length,
Mm-hmm.
then it doesn't matter if the weights are negative, because you can transform them by adding on the minimum weight. If the paths are
Sure,
different
sure.
lengths, then you can't do that.
Sure.
So I was curious if this would work if you had like diagonal steps in your path as well. Like if you were allowed to walk to the right, down, or diagonally down right. Because it seems like I don't see anything that breaks in this recursion if you were to add another else case.
So there are only 2 edges coming out of every node. The more edges you add, the more work this algorithm will do.
But it will still.
But if you just add one more edge, if you're allowed to like go from here to here, yeah, this will work.
And Dijkstra would completely not work on that case.
No, it will too. I mean, Dijkstra is for general graphs.
If you have negative weights.
Oh yeah, sure.
transform
Yeah, forget.
But this one could solve it.
Yes.
Okay.
Yes, but again, it's because it's super structured. And in the worst case, every node could have a lot of edges coming out of it, in which case your dextras will do better, if all positive.
Yeah.
Yeah.
Negative ways if it's acyclic.
So again,
If it's acyclic, it should work negative ways.
I'm not sure. Possible.
Yeah,
Yeah, it should work.
probably works. But this is acyclic.
Yeah, we came out.
This is a DAC. Yeah. So, any other questions? All right, last question. Last example then. So, I think, last example. I think you guys have understood dynamic programming pretty well at this point. But just as a last call. So we're in some foreign country and we have coins. We have n denominations of coins, and we're trying to see if making a particular sum using these coins is possible. So let's say I have denominations, coins C1 through Cn. Right? So the C's are integer values, positive, and we're trying to see if we can potentially get sum S. Right, so if one of the C's was 1, Ci's was 1, for example, then S is also an integer, positive integer, then the answer would always be yes. So this is in the case that you're in some weird country that doesn't have pennies, for example. Right? So it's just a matter of, can I take some number of these, some number of the Ci's, add them up, get S? Right?
One of each, or can you have
You can have as many of each as you like. Right? A positive number. Again, this is really, everything's positive in this. Not even 0, positive. Okay? So anyone see any solution to this? Give me any solution. Dynamic programming, recursion, brute force, whatever.
Divide S by Ci, and that's the maximum number possible for each of those coins, and enumerate every solution.
Maybe all of
Okay,
them-
that would be super slow, right?
No, but all of them first.
Say again?
Try to order them, no? Because you
Oh, I give you them order, sure.
Okay.
So the CIs, let's say they're increasing, non-decreasing. Well, it doesn't make sense to repeat a coin, so just increasing.
Start by removing the largest possible and repeat the problem.
Okay, so that's fair, except that it might fail. It's not actually guaranteed to work. For example, if I gave you the coins 7 and 2, and I gave you 22, you would end up at 1 with 1 left, and you couldn't do anything about it. You would take off 3 7s, and then you'd be left with 1 you need to make up, and you only have 2 and a 7 to do it with.
So you check each of the S minus Ci whether it is possible for S minus Ci for each I.
Yes. So that's it. Yeah. So you say you have this recursive definition of called possible I. Okay. And the question this recursive definition answers is it possible to make the sum I? So we'll just call this with S and get our answer out of it. So this is not the best parameter. Possible. K. Possible K. Okay. And what's this going to be? It's possible to make some K if big or union, if it's possible over CI if it's possible to make K minus CI. And if, sorry, first of all, if K is less than 0, return false. If K is equal to 0, return true. Else do this. Right, so is it possible? It's always possible to make zero sum. You just take 0 coins. It's never possible to make negative sums. And in the other cases, it's only possible if you use one sum coin, and then the rest can be made with other coins. So now, again, this has K possible, sorry, this has big S possible invocations. Right. We'll call this with S, and then, so this has big S possible invocations, and for every single one of them we do n work. So the runtime of this algorithm is big S times n. And again, via backtracking, we could get the actual coins. So here we would just say, okay, to get the sum K, first use a coin CI if one of these turned out to be true, and then call the recursive, and then use that to backtrack to decide what the next coin should be, and then you'll get the string of coins necessary to make the sum K. Now, we didn't just solve the subset sum problem, right? So I don't know, has John talked about the subset sum problem as an NP-hard problem?
No.
So the subset sum problem asks if, given a set of numbers, is it possible to make a particular sum? Right? It seems like we just solved that problem, and we did it in polynomial time, but we didn't. Can anyone tell me why? So
You use the ordering of things.
no, I could. I mean, in the subset sum problem, there's nothing.
You mean in this problem? I thought you talked about the array with the maximum sum. On the window.
You cannot use coins twice in a case, kind of, or
You- Well, this problem is actually more general, right?
Yeah.
So there's nothing stopping me from adding. This problem says, okay, can you? So I could say, I could add another array here saying used this coin and then never use it again.
Yeah.
And so then I'd still have something that looks like maybe an n squared here, because I'd have an extra parameter saying I used the coins up to this point. But the real reason that we didn't solve subset sum is that this guy, S, this is the actual value of S that was passed into the problem. But the problem definition only needs the number of bits that it takes to encode S as input. So what does a computer see when this problem is put into it? It sees n numbers, right? And then it also sees log S bits. Right? So a polynomial time solution would actually mean that you take time that is polynomial in log of S. Not S itself, log of S. So that's what a polynomial time solution would mean in this case. But we're using S. So actually our solution is exponential in the number of bits that it takes to write down the problem. And so we didn't just solve P versus NP. This is only going to work for small values of S. And by small, I mean pretty large ones, like like 1 million, but that's just not good enough as far as the definitions go. And also, you need that much memory too. It's not easy to get 1 million bytes of memory. So, okay, it is. It's very easy. But they make it a little higher, and then it's not easy. It's very, very, very easy. Sorry. I got to be careful with what I say exactly. It's not easy to, bump it up. So, yeah, those are the 4 examples of dynamic programming I got for you. You guys already knew this stuff, it seems.
We wouldn't even need that much memory though, because we only have to go back as far as the largest coin at that point, right?
Yeah, there's 1 million optimizations. This is the most basic. I mean, you don't even need to. You could try the multiple instances of a coin in this itself. So, well, that wouldn't give you much. Yeah, lots of. But there's no way around having this in this simple scenario. The S will always be there. So you just saw 4 very quick dynamic programming examples. Any other questions?
What is the running time S comes in?
So the space of possible parameters that possible, okay, that was all things that could, there are n things that, there are big S things that I could potentially put into possible. This is a function, right? I'm defining it as such, right? This could be called, every single value that k can take on could be realized. And so in the computation of possible of S, it's potentially going to happen that every single value that I can fill in here will be filled. Right? So then I've already done big S work. Right? And then furthermore, every time a call is made, you have to compute this array. So you have to compute this, you have to do all this work. Right? You have to go through every single CI and check to see whether the invocation is possible. Right? So you're doing n work per invocation of this function. And recall that because we're doing memoization, we'll never redo work. So really, the amount of work that you do is just the number of possible parameters to the function and times the amount of work done in each call. That's a general method to figure out how fast a dynamic programming solution is. You look at the parameter definitions. You see, okay, how many things can go in each of these slots? You multiply all those together to get you the possible number of parameters. Then you see how much work is done per parameter, and you sum all that up. In this case, there are S things in the parameter space and N work per parameter. Okay. There is no.